Okay, next part we're going to look at is how we can use an enthalpy cycle, sometimes known as a Hess cycle, to calculate a value for an enthalpy change of a particular reaction. So this sort of picks straight up on that little cycle we did at the beginning when we talked about what Hess's law actually means to do with it. It doesn't really matter which route you get from a particular starting point to a particular finishing point. It doesn't matter in terms of the energy which route you take. The total energy change will be the same. So sometimes we might have to use one of these cycles to calculate a delta HR value. So here's an example. If we've got an equation here where we have got an unknown enthalpy change, so this value here for delta HR is what we want to know at the moment. That's our unknown value. But we may have some enthalpy changes where we do know the values for, and we'd be given those. And what we need to do is think, well, how can we use these values that we do know to work out the one that we don't know? What we can do with this is we can see that if we have this equation, there we go, sorry, that's just that sentence underneath. Okay, we can link these three equations together in what we call a cycle, an enthalpy cycle or Hess cycle. Now, the way that we do this is we write down the equation that we're trying to work out the enthalpy change for, kind of along the top. That's the way I would always do this. So that's this equation here. And then what you've got to kind of do is you kind of look at and see, well, how do these other equations that we've been given and that we do know the values for fit with the one that we've got here? Well, if we look at what we've got in this first equation here for which we've been given the value for, we've got sulfur being converted into sulfur with 3 oxygens on it. So not the same product as the one at the top here, a different product, but it's the same reactant because it's sulfur. So rather than sulfur forming sulfur dioxide, SO2, it can react with oxygen to form SO3. Okay, and what I could do here is actually write this number minus 395 on the arrow, because I can see that that's the enthalpy change associated with that change, sulfur to sulfur trioxide. Don't worry about the oxygens here. We're sort of looking at the key substances here, which are the ones that involve the sulfur, and sort of ignoring the oxygens. Now we can also see, hopefully, from the second equation that we've got here, again focusing not on the oxygen but on the substances that contain the sulfur, sulfur dioxide can form sulfur trioxide as a product. So again, starting there, because that's the sulfur dioxide, so it matches here, can react and produce that one. Okay, it would need some oxygen to do that, and we could put that in if we wanted to, but it doesn't really matter. Okay, and again, what we could do is put the value, minus 98 for this one, on our arrow, the arrow that corresponds to SO2 being converted into SO3. Now what we've got is what we call a Hess cycle or an enthalpy cycle, and we can use this to figure out what this unknown value is by applying that rule we talked about a moment ago, about it not really mattering which route we take if we've got 2 possibilities. So what I tend to do when I look at a Hess cycle or an enthalpy cycle is I look at the substances at each part, so each sort of corner of the triangle. Now, if you look at your Hess cycle, you should always be able to spot where the start of the cycle is and where the finish is. The start is where we've only got arrows leaving, only arrows going out of it. So that's here, because this box here has got an arrow coming out there and an arrow coming out there. So that's kind of our starting point. And the finish, the end point, is the bit which only has arrows going into it. So that is here, because we've got an arrow coming in there and an arrow coming in there. So that's the end. And once you've identified your start and finish, your starting point and your end point, it's pretty easy because we've got one possible route from, it's like going from A to B, start to finish. We've got that route, or we've got the kind of round the houses indirect route. We've got that route. Okay, so we've got route 1 or the alternative route, route 2. Now, because of Hess's law, route 1 is always equal to route 2 in terms of its energy change. So what that means is route 1, with its value of minus 395, is equal to route 2, which has a value of delta HR, whatever it may be, plus the other bit in that route, which is minus 98. And if we rearrange that and do the maths, we should end up with a value for delta HR, this reaction, the one that we wanted to know all along, of minus 297, and that is in kilojoules per mole. Okay.